Let us begin. A student prepares an ethanoic acid solution of a pH of 5. He uses the solution to make a buffer. Lovely. Define each of the following terms pH. Define pH for me, please. Somebody define pH. pH is the pH is go ahead.
Minus log to the base 10 of H plus iron.
Okay. So how do we put that in? Okay. How do we put that in words?
Um, the negative logarithm of the negative logarithm to the base 10 of H plus ions.
Okay. So it's the logarithmic value, right? The negative logarithmic value, right, of the concentration of our hydrogen ions or H plus ions or protons or whatever you want to call it, right? So it's a negative logarithmic value. So I want you to write it out in words, Write it out in words and then provide an equation. Each time in science you do a definition, if there's an equation, you write your equation beside your worded definition. So in case the worded definition don't make no sense, you have the equation. Alright? So it's a negative log. Even for physics, please do that with physics as well. It is important. Write your equations. Right? So once after you finish writing your worded, then you write your equation, right? Now buffer is not an equation for really exemplify it. So what is a buffer? Solution. Go ahead.
Sir, buffer solution is a solution that resists drastic changes in pH when adding uh, small amounts of acid or alkali.
Okay, lovely. That can be accepted. So it's a solution, right? that resists drastic drastic changes in pH when a small amount of acid or base is added. And some people want to go to extra mile and say it's a solution comprising of equimolar proportions of an acid and its salt or a base and its salt, which resists drastic pH changes in pH when small amounts of acid and base are added. Right? If you want to go the extra mile or just do the simple definition, that should get you 2 marks. Alright? The acid dissociation constant Ka of ethanoic acid at 25 degrees Celsius has a numeric value of 1.7 times 10 to the negative 5. The equilibrium equation for the dissociation of ethanoic acid is presented here. Write an expression for the acid dissociation constant of ethanoic acid. So what the Ka would be? Ka is what? Product over reactants, right?
Yes, sir.
Alright, so see. Divided by H3 COOH. Nobody can tell me, so 2010 never easy. Moving on, next question. Calculate the equilibrium concentration of ethanoic acid in a solution that has a pH of 5. Alright, this is question now. Okay, have a go. What is the equilibrium concentration of ethanoic acid in a solution pH? 5. I think this is a catch, This question is very interesting. So how do you get the concentration of our acid from pH?
Sure, your answer?
How you get the concentration of acid from pH?
Sir, base 10 to the negative pH.
Base 10 to negative pH. Alright. So,
or anti-log negative pH.
all right, so anti-log. Wait, but what will give us that? What would that be? That would be that hydrogen ion concentration, right?
Yes, sir.
So the hydrogen ion concentration would be 10 to the negative pH. So after we do that, what we get? This is the anti-log. So 10 to the negative, 10 to the power of negative what? Negative 5, right? Right? That would be 1 times
Yeah.
10 to the negative 5, right? And then since, if this is 1 times 10 to the negative 5, so, sorry, 1 times 10 to the negative 5, if that is 1 times 10 to the negative 5, then this is equal, right? Isn't that so?
Yes, sir.
Therefore, it is x squared over what? We do know the concentration of the acid ions, right? So we're gonna have x squared, or well, it wouldn't be x squared in this case. My bad. X would be on the bottom, alright? So we're gonna have 1 times 10 to the negative 5th power all squared. We're gonna minus that 2 from up there. So sorry about that. I mean, above that 2, right, will give us our acid concentration, right, if we figure out how to transpose this times 10 to the negative 5, right? So when we transpose, it's supposed to get x, right? Does that make sense?
Yes, sir.
Do we agree with this approach? You may have a different approach, but do you agree with this approach?
Yes, sir.
All right, so x is going to be equal to what? Transpose x is equal to what?
Sir, x is equal to 1 times 10 to the negative 10 over 1.7 times. Sir, I can't see that number.
Okay, we're gonna write it.
Oh, it's right there. 1
mhm.
times 1.7 times 10 to the negative 5.
All right, go ahead. All right, Riri, go ahead. Somebody raise their hand. Go ahead.
Sir, some people don't understand it fully.
Okay, all right. So what we're saying here is that we need to use the pH to find ethanoic acid concentration, right? We have our Ka expression up here, right? We do have our Ka, but we don't have anything else to find our acid concentration. So what we need to do now is find what we can do is find one of the concentrations of these up here of the products, because we know the concentration of the products will be equal, right? Because if we look at ice tables, if this decreases by x, this will increase by x, and this will increase by x. So they will increase by the same amount, therefore their concentrations will be the same. Therefore, if we find the concentration for one, we find the concentration for both. In this case, we're looking at it in equilibrium. Therefore, the only way only one we can find concentration for would have been the hydrogen ion, right? And if pH is a negative log of the hydrogen ion concentration, right, then the hydrogen ion concentration is the anti-log of the pH here, right? The anti-log. How do you anti-log? You can either shift log whatever you're doing on your calculator, or you can just take 10 to the power of negative pH to find the hydrogen ion concentration. And after you find that, we have stated before that they shall be equal at equilibrium. Therefore, acetate ion concentration will also be the 1 times 10 to the negative 5. So all we do is square the top, because those will be the same equilibrium. It's 1 times 10 to the negative 5 times 1 times 10 to the negative 5. So that's 1 times 10 to the negative 5 squared, right? And then we divide it by the unknown concentration. We don't know, so we call it X. And then that will be equal to our Ka that is provided. All we do now is transpose. Does that make more sense? Okay, it is almost time for unit 2, so probably we'll just complete these two and then call it a day. Alright, or I'll try to complete the rest of them at a later date, probably tomorrow. Alright, so calculate the equilibrium concentration. X is equal to what again? X is equal to 1 times 10 to the negative 5.
So 1 times 10 to the negative 10.
Yeah, to the negative 10 technically. Okay, to the negative 10. Because if you square it, it's going to give us negative 10. And then divide it by 1.7
over 1.7 times 10 to the negative 5.
And what is our value? What is our answer? Not 1.1.
5.88 times 10 to the negative 10.
Negative 10, interesting. Alright, so it is going to be. How did you get negative 10 as your final answer? Go ahead.
I mean negative 6, sir.
Okay. Times 10 to the negative 6. Alright. Concentration.
So I got 5.8 times 10 to negative 6.
Lovely. Alright. So wait, hold on, You'll still only get 3 marks for this. And why? What is missing?
The units.
The unit. And the unit of concentration is?
Moles per dm cube.
dm cube.
Lovely. Alright, moving on. State the effect on the equilibrium position of a buffer solution of adding small amounts of acid or bases. So you need to know the effect on the equilibrium. So if we add small amounts of acids, what will happen to the equilibrium position? Go ahead.
Okay, sir. So for the acid, for the acid, it will form more. When you add the hydrogen ion, sir, it will form more water, sir. So the conjugate.
Hold on, just to fix that a little bit before you continue, because I want you to continue. But the hydrogen ions won't actually form water, because remember that the base is present. So the conjugate base will actually take up the hydrogen ions. So you're not going to have water being formed. But go ahead.
Sir, sir, that's where I'm confused. Sir, how does water come into this?
When the okay, so if you have excess, let's go back to 2008's paper with acid being added here, right? If we add an acid here, it's a base that will take up the acid, right, and provide us with will take up the hydrogen ions and reform our acid, right? And if we had a base now, like hydroxide, it is our acid that will donate its proton to the hydroxide to form water. So it's in the hydroxide now. We add base, that's when we have water being added. And then when we add acid, that is when we have our original acid molecule being reformed. Right? So what's gonna be happening is shifts. Right? So when we add acid, we are gonna be shifting the equilibrium to the towards the acid, and we're adding base, we're gonna shift the equilibrium towards reforming the base. Remember, there are reformations, right? Reforming this and reforming that. If you look at it, if you write it, we tend to have acid and water gives us base. Let me go back. Let me reshare 2008 paper. Right? We tend to have acid. Here's the acid and the water. Right? We tend to have those two. Let me do it here, right? So HA is our acid, and here we have our water, and it tends to give us this is our conjugate acid here, and this is our would that be our conjugate acid? Well, that would be a conjugate. You guys never realize that never work out. This would be a conjugate base. This would be a acid. This would be a conjugate base, right? So what's happening? We have our main acid molecule, right? And that's going to be in water, dissolved in water, to give us our hydronium ions on our conjugate base. So when we add acid, we're gonna be the acid is actually gonna be added, right, to our conjugate base over here, and it will reform our original acid molecule. Because if the lactate gains back an hydrogen, it's going to become lactic acid. So that is not when you have water formed. You have water formed when you have OH being added now. Because when you have OH being added now, then our lactic acid now will lose its proton to our OH to form water. And then that will form our conjugate base. But yet again, if you want an in-depth exploration of how it works, I could send a link to the YouTube video for you, because we went over it with the acetate bubble system. All right. The last question. Technically, I should end right here because Unit 2's time would going into Unit 2's time, but I am going to send a link to them right now, and we'll try to finish this question. All right. So a buffer solution is made by adding 20.5 grams of sodium ethanoate to 500 centimeter cubes of 1.5 mole per dm cube of ethanoic acid. The Ka is 1.7 times 10 to the negative 5, right? What's happening here? What is it that we do first? Hold on, let me. Oh my gosh. Go ahead. What's the procedure?
So, sir, the first thing we would do is find the molecular mass for sodium ethanoate.
Mm-hmm. So find molecular mass, then
Finding the molecular, would find the number of moles of sodium ethanoate.
lovely. Then
then we would write or so what do you call the thing with the salt over the acid?
and the Sansbach equation. Wait, the salt over the acid. What are you talking about?
Yes, sir. No, sir. That's a part of the equation, but
So
we'd write the Henderson-Hasselbalch equation, sir.
okay, then we do the Henderson-Hasselbalch equation. I want to calculate the pH of. Okay, so let's say the first thing, right? I can only do this, and then I'm going to continue with the Unit 2s after this, right? So the first thing, we have the mass, right, of sodium ethanoate. So we need to find the molar mass of the substance, and then we can use that to find the number of moles. Right? So after we find the molar mass, we use the molar mass to find the number of moles. You know the equation. I won't insult your intelligence, right? You know the equation, right? So after we find the number of moles now, what we're going to be doing is dividing the moles that we get by 500 centimeter cube times 1,000, because obviously you need it in dm cube to get the molar concentration of sodium ethanoate as a salt, right? And then we put that concentration, right, as well with the acid concentration and the Ka, the pKa of the acid, which is a negative log of 1.7 times 10 to the negative 5, into the Henderson-Hasselbalch equation, and that is your answer. Hopefully that makes sense. We need to find the molar concentration of sodium ethanoate. We need the salt concentration. That is what we do not have. So in order to get the salt concentration, we need to find the molar mass of sodium ethanoate, use that to find the number of moles, then divide it by the 500 centimeter cube when it's converted to dm cube. That is how we get our salt ion concentration, right? And then after that, now we negative log the Ka to get the pKa, and we'll plug it in. Go ahead. Sean J, go ahead.
Sir, won't you have to, won't you have to divide the molar mass of sodium ethanoate by 20.5?
Yes. Mm-hmm. Is that how it's done?
All
Mass
right.
divided by, wait, is mass divided by molar
Yeah,
mass
because
gives you
I
moles?
see.
Yeah. Mm-hmm. Mass divided by molar mass gives you moles, right? So after you get the number of moles, that's what you do. So you get the number of moles, and the only volume we have here is this same volume. And remember that our buffer of solution is in the same thing. So the same volume that ethanoic acid is in, you will dissolve it back into the same solution in order to create your buffer solution. And then after you do that now, you plug it in the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the logarithm of salt ion concentration divided by acid concentration, and that is your answer. All right. So I want you guys, if you guys want to, I want you guys to try it, send answers in the WhatsApp group, and we'll look at it. So take a screenshot, and then we'll look at the answers. All right. So that was the 2010s. Well, sorry, 2010. Hello. That was 2010s buffer systems question, right? So buffer and pH questions. That is it.